Hi guys, welcome to the video tutorial for chapter 9.5. We're looking at the Doppler effect with respect to light. So let's get right into this. So our first learning objective is to appreciate that the Doppler effect is responsible for the observed shift in frequency of light coming from distant astronomical bodies. So mostly we're talking about stars here in terms of distant astronomical bodies. And this is related to Einstein's theory of special relativity. So one of the special things about the theory of relativity, or equals to mc squared, states that objects cannot travel faster than the speed of light. There's no y. Well, there is a y, but we'll get into that a little bit later. So first off, let's maybe just quickly review the Doppler effect. And so the Doppler effect is the idea that either a source is moving towards or away from an observer, or in the other situation, the observer or the source is the observer is moving towards or away from the source. And so we've got two equations in your data booklet, as you can see below here, and they are labeled moving observer and moving source, but you need to distinguish the plus and the minus about what happens there. In both cases, you can actually see that we are adding the speed of the observer, UO, observer, or we're adding the speed of the source, S for source. Now, the funny thing, or the strange thing about light then is that even if, let's say there's a guy here and he's got a torch here, and he's running towards another person. Now, technically speaking, the speed of light is going it's going at the speed of light, c, and with this person's extra movement, the velocity of the source, we are technically we should be adding these two speeds together. Now, because of this limitation that light cannot go faster than the speed of light, this then causes the other things to change, right? So we know c equals to f lambda. So what we're really saying here is that this is now capped. This is constant, so we can't go any faster. So what has to happen then is the frequency and the wavelength will then shift as a result of that. And so what we observe is the following thing. In a non-moving situation, so I guess the closest thing we have to an object that's, in theory, not getting any further or closer to the Earth is the moon. Okay, well, I mean, it might be, but it's so small that we, in comparison to other objects that are actually moving very far away from the Earth or moving very much closer to the Earth, we consider something like the moon to be non-moving. Okay, but that doesn't really happen very often, but it helps us give us a frame of reference. Now, when a star is moving away from the Earth, it undergoes what we now see as redshift. And if you Google, if you look at, let me see here, if I get, okay, so internet is still coming online here. But if we Google a picture of the universe, my Wi-Fi is not cooperating with me. Come on, Wi-Fi. Okay, I'm just gonna hope that reconnects. Okay, I'll get back to that a little bit later. Just give it a moment to connect. So redshift is what happens when a distant star moves away from the Earth, and blue shift is when it moves towards the Earth. So as you can see here, the waves either stretch out, so the wavelengths will get longer, or the wavelengths will get shorter, they'll compress into each other, resulting in redshift and blue shift. Now, it's normally the frequency that we actually talk about. So we say the frequency increases or the frequency decreases in this particular case. Okay, so actually I'm going to jump down to the third learning objective, which is sort of related to the first one, but then they're all sort of related together. But I think this will kind of help us frame what's going on there. This is sort of the why of of the question before of why can't an object go faster than the speed of light? Um, and so without looking at the formula for now, we're trying to observe this fact that um, the recession speed, or the speed of the celestial bodies, stars essentially, cannot approach the speed of light. And again, it's due to this theory of special relativity. And what it's essentially saying is that as an object moves towards the speed of light, it requires more and more energy in order to propel it, to move it at that particular speed. And so we get into a situation where it's impossible, at least for now, to generate that much energy to cause massive objects to approach or to reach the speed of light. The physics that we know that Einstein has outlined essentially says it's impossible for that to happen. And so it might be helpful to first think about a photon. So a photon is massless, and as a result, because it is massless, it is able to travel at the highest speed in the universe, the speed of light. A star, on the other hand, is probably on the exact opposite end of that, okay? The star is massive, okay? In fact, our sun is on the order of magnitude of 10 to the power of 30 kilograms. And so if we try to move an object like that towards the speed of light, it requires way too much energy. And that essentially it becomes impossible to do that as a result of the equation equals mc squared. So what we're really saying here is that as the mass increases, the energy must also increase if this remains constant. And as a result of that, it becomes impossible to do something like that for objects on the magnitude of a star. All right. Okay, so that's the third learning objective. So we're going to go back now, and I'm going to see if we can get this up again, if my Wi-Fi is working. My Wi-Fi is not cooperating. I'm sorry, guys. I would encourage you to Google a picture of the universe. And what you should see is you should see a lot of red galaxies, and you also see a lot of blue galaxies, okay? And so blue galaxies are moving towards you or towards us on Earth, and red is moving away from us, okay? And so the colors of the stars that we see give us information about what's actually happening in terms of motion. And this is all from the study of the Doppler effect. Okay, so let's get into some calculations here of using the formula. And so if you just want to backtrack to the previous section here. So a lot of this is actually looking at this relationship of a new frequency is the old frequency, and then there's a change of velocity over velocity. So that really is what these formulas boil down to. And associated with that as well is also a change of wavelength as well. There is another equation, you guys have to backtrack to that. And so this formula, the three things are given as ratios of each other, essentially. So maybe let's go into a calculation to see what is going on with the second learning objective of using this formula. So stars observed through a telescope on Earth. The wavelength of light that is emitted by the star is 400 nanometers. The telescope passes the light through diffraction grating, and the wavelength is measured as 403 nanometers. What is the receding speed of the star? So we already know that it's already telling us that the star is moving away from us. It is receding. So first off, the wavelength, or the original wavelength, is 400 nanometers. And the new wavelength is 403 nanometers. And so the change of wavelength is the difference between these two guys. Sorry, that's not lambda. So lambda prime minus lambda, which is going to give us 403 nanometers minus 400 nanometers, which is essentially just 3 nanometers. And the velocity is what we're looking for. So I'm going to write a question mark for that. And so we're looking at this. This is unknown. This we've got. And we've got our change of of wavelength and also the original. So purely just a substitution now. I'm going to rearrange this formula on its own. So I'm going to move that over here, get rid of that. I'm just going to move this over to the other side. Sorry, I'm going to rearrange this formula. Okay, so this is what we're looking at here. Okay, so now that I've got the formula rearranged, we're going to do our substitution. So this is 3 nanometers times the speed of light c over the original, which is 400 nanometers. Okay, so the nanometers will cancel each other out. And so it's really 3 over 400 times the speed of light. So 3 over 400 times the speed of light, 3 times 10 to the power of 8. And we get 2.25 times 10 to the power of 6 meters per second. Okay, and that's not too bad. It's definitely less than the speed of light, 2 powers less, and so that sounds about right. Okay, so it's moving quite fast, obviously, but it's nowhere near the speed of light. Okay, another question here is we have a sample of hydrogen on Earth. This is from the section questions, by the way. So a sample of hydrogen on Earth emits a spectra line with a wavelength of 620 nanometers. So I'm just using different colors here. So 620 nanometers, so that's the original. We're looking for lambda prime, as I've already got here from before. And the speed is 5%, not 50%, 5% of the speed of light is how fast the object is moving. And so I've already done the formula rearrangement here. Okay, so we just kind of select the sections that we've got. So we've got wavelength, so that's why we grab this section there. Okay, and we're looking for the speed, so we grab the speed section. So those 2 particular parts is what we've got. Okay, so let's get into our substitution. So the wavelength is 620 nanometers. The speed is 0.05 times the speed of light divided by the speed of light. So the speed of light cancels itself. And so it's really 620 times 0.05. So it's 31 nanometers. So that's the change. And so recall earlier here that the change is the difference between the two. And so I'm going to squeeze that up here, the extra little bit of work that we're going to do. And so we have the change, which is 31 nanometers, which is what we calculated, right? This is equal to that. So 31 nanometers, and we're looking for lambda prime. And we need to subtract that from the original, which is 620. So essentially, we're adding the 2 together, 620 plus 31. So lambda prime is 631 nanometers. Okay, so that's the solution, guys. Pretty straightforward. Keep some of the units because a lot of times they cancel each other out. As you can see, the C cancels out here and before the nanometers cancels out. Okay, so that makes it pretty nice. Okay, guys, short lesson today. Have a great weekend or have a good holiday, and we'll see you guys when Easter's over.